All aircraft are designed for specific weight limitations and balance conditions. An overloaded aircraft may cause structural failure or result in reduced engine and airframe life. An unbalanced aircraft may create longitudinal, fore and aft, instability. Since both weight and balance have a direct bearing on performance and control, a pilot should never fly until he is completely satisfied with his aircraft's loading. If he does, he is only inviting disaster. Now, to calculate the balance status of an aircraft, you must first have a working knowledge of the principle of moment. During this program, you will learn how to compute moment, the effects of moment on an aircraft, and how moments are used to calculate an aircraft's center of gravity, or CG. Now, what does the phrase principle of moment mean? A moment is the product of a force or weight in an aircraft times a distance. The distance used in calculating a moment is called the arm and is usually expressed in inches and is measured from a desired known point on the aircraft referred to as the reference datum line, or RDL. In order for an aircraft to be in balance, the sum of the moments on each side of the balance point, or RDL, must be equal, which is the principle of moments. To demonstrate this, compare the profile of this helicopter to a lever which has been placed on a fulcrum. The pivotal point equal amounts of the lever on either side. The numbers will designate the distance out from the pivotal point in inches. The reference datum line, or RDL, is placed over the pivotal point. As you recall, the RDL is the line from which you make all measurements for weight and balance purposes. With this lever, you have two possibilities of rotation. The first is clockwise rotation, indicated as a plus or positive value. The other, of course, is counterclockwise rotation, which is designated as a minus or negative value. These signs are used to differentiate between the turning motion of the two sides. You can see that this lever is in balance because you have equal amounts on each side of the RDL. So with the aircraft, of course, you are mainly interested in balancing it about a certain point. Now, to demonstrate this, we'll take 100 pounds of weight and place it on the clockwise side 5 inches out from the RDL. Realizing, of course, with this weight on the clockwise side and none on the opposing side, the lever will rotate in a clockwise direction. In weight and balance, you must have a means of determining the measure of the rotating force created by any weight. You can do this by using the moment formula. Weight times arm equals moment. To determine the turning effect produced by this weight, 100 pounds, at this distance, 5 inches, substitute the values into the formula and multiply them out to get the moment. A 100-pound weight times a 5-inch arm produces 500 inch-pounds of moment. Thus, the turning effect is 500 inch-pounds in a positive direction. Now, to balance out the lever, the easiest way would be to put the same amount of weight, 100 pounds, at the same distance out on the opposite side. So, by using the formula again and substituting the values, a 100-pound weight times 5 inches out, you come up with 500 inch-pounds of moment, proving out mathematically that this lever is now in balance. The law of moment states that for a state of equilibrium, the sum of the total clockwise moments must be exactly equal to the sum of the total counterclockwise moments. With an aircraft, however, you do not always have the same amounts of weight to place, nor do you always have the same distances available to place the weights. Yet you must come up with a balanced condition. So let's use the lever again and show how you can have different weights at different distances and still come up with a balanced condition. Let's remove this 100-pound weight from the counterclockwise side and replace it with a 125-pound weight. Now you need to figure out where to place this 125-pound weight to balance the lever. First, you have a couple of known factors. You have the weight, 125 pounds. However, you do not know the distance out to place it. But you do know that you must create 500 inch-pounds of moment as indicated on the clockwise side, equal amounts of moment on both sides. With your two known factors, you can figure the unknown. It is a matter of dividing the known factor, weight, into the known moment required, inch-pounds, and this will give you the number of inches out to place the weight. So 125 into 500 would produce an arm of 4 inches. Substituting the arm of 4 inches into the formula, 125 pounds times the 4 inches gives you the required 500 inch-pounds. Therefore, if you place the 125-pound weight at 4 inches out on the counterclockwise side, you will then have a balanced lever. Consequently, you can have unequal distances and unequal weights and still be able to come up with a balanced condition. With this type of lever, you have been concerned with positive and negative moments. Dealing with negative and positive values in a mathematical computations creates more room for error. When you use these same principles to determine an aircraft's center of gravity, this room for error has been eliminated. This is due to the placement of the RDL, which is usually located at or near the nose of the aircraft, to eliminate arms with a negative value. Earlier, you were working about a given pivotal point to balance a lever. But with an aircraft, you want to determine where the center of gravity is after it is loaded, and if it falls within the center of gravity limits. When this has been determined, your aircraft is then perfectly balanced for flight. To demonstrate this principle, let's use a board 20 inches in length. Now, the first thing we must do is to establish an RDL. For this demonstration, the RDL will be located to the extreme left. You can see how the minus distances and minus moments have been eliminated. All dimensions and moments now become positive. Now, let's say this board is lying on the floor, and we'll put some weights on it, determine its center of gravity, and then support it at that point on a fulcrum. First, we'll place a weight 20 pounds, 12 inches from the RDL. Next, a 10-pound weight 9 inches out. And lastly, a 15-pound weight 5 inches out. Now, you have 3 weights applied to the board. No matter how many weights you might have involved, the principles are still the same. Next, determine the moment created by each individual weight. With weight and balance, you cannot sum up a series of arms and weights and multiply them out and get the same result. It will not give you the correct answer. Instead, each item must be handled individually. So, using the moment formula again, weight times arm equals moment, substitute your values and multiply them out. The 20-pound weight times the 12-inch arm produces 240 inch-pounds of moment. The 10-pound weight times the 9-inch arm produces 90 inch-pounds of moment. And the 15-pound weight times the 5-inch arm produces 75 inch-pounds of moment. Now you will have to add up the weights and moments and apply them to another formula. When you sum up the two columns, you come up with 405 inch-pounds of moment and 45 pounds of weight. With the total weights and total moments, you can insert these values into the center of gravity formula to find the center of gravity. Center of gravity is the total moments divided by the total weight. Substituting your known factors into the formula, 405 inch-pounds divided by 45 pounds will give you a center of gravity of 9 inches. 45 into 405 goes 9 times. Your pounds of weight into pounds of moment cancel out, leaving you with inches. So your center of gravity is 9 inches from the same reference point from which all your measurements are made. Remember, in any weight and balance problem, you must use the RDL in the same position, and all measurements, including the final center of gravity, are measured from that point. Should you pick up this board and place it upon a fulcrum, 9 inches from the RDL, the board would balance. This is the balance point, your center of gravity. This principle applies exactly the same to an aircraft. Using the outline of an aircraft, let's place some cargo aboard it, determine the moments created by the cargo, and then determine if the aircraft's center of gravity is proper. You must first establish a reference datum line. This information, which has already been determined by the manufacturer during the design of the aircraft, can be found in the aircraft's operator's manual. All measurements have been made from this point, so for weight and balance purposes, you must make all measurements from this point. As mentioned earlier, the RDL is usually located near the nose of the aircraft. For aircraft loading, the distances from the RDL are referred to as stations. For demonstration purposes, let's use a U-860 Blackhawk and place a 50-pound weight at station 285, a 120-pound weight at station 315, and finally at station 365, a weight of 60 pounds. Now it is just a matter of finding the moment created by each of these three weights. First, you have the 50-pound weight at station 285, producing 14,250 inch-pounds of moment. Then you have the 120-pound weight at station 315, creating 37,800 inch-pounds of moment. And the 60-pound weight at station 365, producing 21,900 inch-pounds of moment. Now that you have the weights and moments of the cargo, it is necessary to add these values to the basic weight and basic moment of the aircraft, which is established on Chart C, DD Form 365-3 by any given aircraft. These are the base figures from which you work. So the basic weight of this aircraft is 13,692 pounds, and the basic moment is 4,987,000 inch-pounds. Below these two values, you see the weights of the three pieces of cargo and the moments created. Summing up these two columns of weight and moment, you'll find that you have a total weight of 13,922 pounds and a total moment of 5,060,950 inch-pounds. With these values, total weight and total moment, simply insert them into the CG formula to determine the CG. Total moments divided by total weight equals center of gravity. Substituting in the formula that 5,060,950 inch-pounds of moment divided by 13,922 pounds of weight will produce a CG of 363.5 inches, which is now the aircraft's center of gravity after it has been loaded. Now you will need to check the CG limits of the aircraft specified in the aircraft's operator's manual to see if your center of gravity falls within the limits. For this particular aircraft in weight, the U-860, the CG limits are stated as 343.2 inches forward and 366.0 inches aft of the RDL. You determined your CG as being at station 363.5, which, as you can see, falls well within the 343.2 and 366.0. This aircraft is now safely loaded and balanced for flight. This program has briefly explained the procedures involved in determining weight and balance of an aircraft. With a better understanding of the principles of moment, you should be able to properly load your aircraft within the proper weight limit and balance range